Okay, so the addition law of probability, we're going to now make a connection kind of between our first topic was on sets and looking at intersections of sets and unions and complements. We've been using complements, right? But we haven't really talked about the intersection and union and the stuff we did with Venn diagrams. We haven't really applied that to probability, and so this is where some of that starts to connect. So I'm going to read through this first, and you can read along. So the addition law, as we have already noted, the sample space is the set of all possible outcomes of a given experiment, and that's we defined that in the last section. Events A and B are subsets of S, so an event is a subset of your sample space. In the previous section, we defined what it was meant by P of A and P of B. That's notation for probability, and they're complements in the particular case in which the experiment had equally likely outcomes. And that was key for the last one. That's what made it elementary probability, that each thing was equally likely that we worked from. Eventually, we're going to move away from that, and we'll have to handle those things a little differently. So recall that the notation AUB denotes the event A or B or both, right? That's the union, and the word or kind of go together. Also, remember that the intersection and the word and kind of go together. So in this section, we obtain the expression for determining the probabilities of these combined events as the probability of A union B or the probability of A intersect B. So let's take a look now at this first example. So a bag contains 18 colored marbles, 4 are colored red, 8 are colored yellow, 6 are colored green. A marble is selected at random. What's the probability the ball chosen is either red or green? Not too hard, right? Assuming that any marble is as likely to be selected as any other, so we're still working with the equally likely outcomes right now. The probability that a chosen marble is red is 4 out of 18. You guys good with that? Because there's 4 red marbles out of the 18. And the probability that it's green is 6 out of 18. And so it follows that the probability that a ball chosen red or green is 10 out of 18. Making sense? Okay. They just add them, right? In this case, we can do this because the events are mutually exclusive. And that's going to become important for us. And remember, with Venn diagrams, mutually exclusive was the case where there was no intersection. They didn't have anything in common. You can't pick a marble and it be both red and a green marble at the same time if you're only picking one marble. Okay? Now, let's compare that to this next example. Because in this next example, something different is going to happen. How many have played with cards? Actually, I should say this. How many have never played with cards? Okay, good. So you guys have some background. Because with probability, there's a lot of probability questions with cards, and we'll be getting into those more in next section, and I'll refresh your memories if you don't remember all the details about cards. But here's a card example. Consider a pack of 52 playing cards. A card is selected at random. What's the probability the card is either a diamond or a 10? Okay, so the probability that it's a diamond is 13 out of 52 since there are 13 diamonds in the pack. Good with that? The probability that the card is a 10 is 4 out of 52 because there's 4 10s in the pack. But if I want the probability of one or the other, am I going to add these like I did in the last problem? No, I'm not, because it's a different kind of thing. In fact, these are not mutually exclusive because they do have an intersection, right? If I look at the intersection, so if we talk about diamonds and we talk about 10s, is that what it is? We have one card in that intersection, the 10 of diamonds. So these are not mutually exclusive. You can have one card and it be both in this case. And so what happens here, there are 16 cards that fall into the category of being a diamond or a 10. 13 of these are diamonds, and there is a 10 in each of the 3 other suits. Does that make sense to you? Get the 13 diamonds, one of them is a 10 already, so there's only 3 other 10s that we need to include in. Therefore, the probability of the card being a diamond is 16 over 52, not 13 over 52 plus 4 over 52. So we need to be careful. So we say these events are not mutually exclusive. We must ensure, in this case, not to simply add the 2 original probabilities. So when it comes to these OR problems, we have to always ask the question, am I working with mutual exclusive or not? Because we're going to have to handle them differently. And here are the 2 ways we handle them. So if the 2 events are mutually exclusive, then we're just simply adding them. If they are not, okay, by the way, let me put this here. Mutually exclusive means that the probability of A and B is equal to what? If A and B are mutually exclusive, what's the probability of A and B happening? Zero, because mutually exclusive means they can't happen at the same time. Okay? So if you're wondering, are they mutually exclusive or not, check. What's the probability of them both happening at the same time? If it's 0, then it's mutually exclusive. So the second formula works actually on every case. So if you're not sure, you want to, this is your default formula, okay? By default, always go to this one, because this works on all cases. Because if it's mutually exclusive, what happens to this part? It goes away. And then you get that formula, right? So this one always works. It's our default. And in particular, if we used it with our cards, we'd have 13 out of 52 here, plus 4 out of 52, minus the probability of getting the diamonds and a 10. What's that probability? How many 10 diamonds are there? 1 out of 52. And then you're finally getting the right answer, 16 out of 52. Okay. All right. Is this making sense? Okay. So I'm going to do a couple problems with you, and then the rest will be homework for you. Okay, so let's start with 2. A bag contains 12 red, 3 blue, 6 green, and 4 yellow marbles. If a marble, so just one, because eventually you'll be picking 2 marbles or 3, but if you're just picking 1 marble from this bag at random, what's the probability that the marble will be either blue or yellow? Okay, so first question we asked, are they mutually exclusive? And I heard a yes. Why? Perfect. So this is yes, so it's an easier one to work with. Okay, we just add it together. And so we're going to put this together. We want the probability of blue or yellow. I'm just going to use the union just to remind you that means or. Okay, so blue or yellow. It's not spelling the word by. Okay, so that's going to equal the probability of blue plus the probability of yellow, because they're mutually exclusive. Now there are 3 blue out of how many marbles? So if we count them, we get 25. So So 3 out of 25. And then yellow, there are 4 yellow out of 25. And so we get 7 out of 25. But we look at our answer choices and they're all percentages. Percent means what? Over 100. So if I multiply top and bottom by 4, I get 28 out of 100. So it's 28. Making sense? Okay. Let's go now to number 10. So number 10 is the first one where we're finally taking the context out. We're just talking solely about probability. And I want us to find the probability of B if the probability of A is 0.5, the probability of A and B is 0.3, and the probability of A or B is 0.6. Okay, so let me start with this. Are they mutually exclusive? I heard no and I heard yes. So can somebody raise your hand and tell me what you think and why? Perfect. Did you everybody hear that? If it's mutually exclusive, then the probability of A and B has to equal 0, but ours doesn't, so it's not mutually exclusive. Okay, so what's the formula we need to fall back on? Probability of A and or B is equal to the probability of A plus the probability of B. Keep going. What comes next? Minus the probability of A and B. So this is one of those formulas you want to memorize, okay? And then plug stuff in. So we know this is 0.6. Probability of A is 0.5. Probability of B we don't know, we're looking for. If you feel more comfortable, you could even do this. You could change that to X because we're just solving for a variable. Minus 0.3. Right? And see if we can find out what X is. And so 0.5 minus 0.3 is 0.2, so it's 0.6 equals 0.2 plus X. What's X going to be? Equals 0.4. And remember, X represented our probability, so we'll finish this by saying the probability of B is 0.4. Are you guys following this? Yeah. Probabilities are always between 0 and 1. If you get a negative probability, there's something wrong. Okay. It could be 0, it could be 1. So we include those, but never outside that range. Okay. Now, if I draw a Venn diagram, we can represent our probabilities in here. So probability of A, probability of B right here. And what would go in the intersection? 0.3, because that's the probability of A and B. What would go in the part in circle of probability A, but it's not in the intersection? Well, 0.5 is the total circle. So 0.2, because they should add up to 0.5. And what goes in this white space here? 0.1. And because it should make sense, because the probability of B is 0.4. And if I add all three of them up, what do I get? 0.6, which is the probability of A or B, because that's the shading of everything. Right? Remember the Venn diagrams? And what would go on the outside? What number though? Point. Well, if this adds up to 0.6, all four of them will have to add up to 100%, and so it's going to be 0.4. And so you could use Venn diagrams for probabilities. You could also use tables for probabilities. You could say like the probability of A, the probability of the complement of A, the probability of B, the probability of the complement of B. Grand total is 1. And so in this problem, it told us the probability of A was 0.5. I'd put that here. We're looking for the probability of B. I'd put an X here. It tells probability of A and B is 0.3. And the probability of A or B is 0.6. And so the 0.6 is the sum of these three, because that's A or B. And so then if I work with the table, I'd say, well, this has got to be 0.2. And if all three of these add up to 0.6, this one's got to be 0.1. And now if I'm looking for X, that's 0.3 plus 0.1, so that would be 0.4. So that's another way to solve it without the formula. So I'm just, again, I'm making a connection between what we did with sets and what we're doing here, okay, for that problem. So it's fun to put those there. All right, I want to do one last one with you, number 12. A spinner has 8 equal sections numbered 1 to 8. What is the probability of the spinner stopping on a multiple of 3 or a number greater than 5? Try that one out. Try it out. So on 12, I'm going to ask you the question again. Are they mutually exclusive, the events? And I'm hearing a lot of people say no. Why not? Okay, because the number 6 fits both categories. It's bigger than 5, and it is a multiple of 3. So let's let multiple of 3 be event A, and a number greater than 5 is going to be event B. And so the word or is being used, so I want to find the probability of A or B. And so that's the probability of A plus the probability of B minus the probability of A and B. And so what's the probability of A happening? A is the multiple of 3. There's 2 out of 8. I'll leave it 2 out of 8. And then probability of B would be 3 out of 8, because there's 3 numbers bigger than 5. And then what's the probability of both happening at the same time? 1 out of 8, which is going to be, add that up, you get 4 out of 8, which is 1/2. Okay. Now, on this problem, is there an easier way to do it than this? Yes. Okay. You just count, right? You got 4 out of 8. So that's the elementary probability, right? The counting and getting at. Sometimes the elementary probability is better than this. But I'm just using this right now because this is new to us, and I want you to see it over and over again, because this will serve us with some tougher stuff when we get to where the elementary stuff won't fit. Okay. So I'm going to stop there and let you have the remainder of the time working through these problems. Okay.